Up until this point, all of our solutions to our systems have been one single ordered pair, so there's been one solution to each of our systems of equations. Just like though when we were solving a single equation, there were sometimes special solutions, that's also true when we're solving a system. So sometimes instead of having a single ordered pair x and y, that is a solution to the system, sometimes we have a special solution, like in this toolkit, no solution. So this system of equations, y equals 2x plus 1, y equals 2x minus 5, has no solution. I'm going to start by solving that using y1 equals y2 to see what that looks like. So again, the two y's are equal at the solution, which allows me to write this equation. 2x plus 1 equals 2x minus 5. This may seem familiar from our equations unit, and it should be. So when I subtract 2x from both sides, the x term in both expressions disappears, and I'm left with 1 equals negative 5. A statement that it does not matter what x is, the statement is never true. 1 does not equal negative 5. What that tells me is there is no solution to this equation, and therefore there is no solution to the system. That's my answer, no solution. If I graph this, so let's see, y equals 2x plus 1. This one right here is this line, y equals 2x plus 1. I'm not really sure that this is important, which one is which, but start value of 1, up 2 over 1, up 2 over 1. Here's my second one, y equals 2x minus 5, start value of negative 5, up 2 over 1, up 2 over 1. And what I have here is a set of parallel lines. This is the big idea here. The reason that this system has no solution is that I have a set of parallel lines, and parallel lines never intersect. There's no intersection point. There is no ordered pair that exists on both lines, and therefore this system has no solution. So the way we can identify parallel lines from the equations, we have the same slope, different y-intercepts, same slope, different y-intercepts. That makes them parallel. They never intersect, and there's therefore no solution. If we are just given a table and asked to identify the solution, we can see that they are parallel lines two different ways. One way is to verify, yes, same slope, plus 2, plus 2, plus 2. This equation also has a plus 2, plus 2. So we know that they have the same slope, but they also need to have different y-intercepts, which they do. 1 and negative 5, that allows me to see, hey, this table represents parallel lines, and therefore it is a no solution situation. We can also look at the fact that the y values stay a consistent distance apart. So depending on which one I'm looking at first, y2 is 6 less than y1, it's 6 less, it's 6 less, it's 6 less. They're neither getting closer together or further apart. y1 and y2 always remain 6 units apart, and that also tells me that I'm looking at parallel lines. So these tables are important because sometimes you'll just be given a table and be asked to find the number of solutions or the solution. So from equations, we can tell no solution by same slope, different y-intercept. Same thing from a graph, same thing from a table. When we are solving algebraically, we'll get to that case where a constant equals another constant, but they're not actually equal. And in any case, the big idea here is this system has no solution.